Hi everybody, my name is Matthew Moreno. I'm a graduate student at Michigan State University working at the NSF Beacon Center, and I'd like to share with you a recap of the presentation I gave at the 2018 GECCO conference on my work with Dr. Wolfgang Bonzoff and Dr. Charles Ofria using autoencoders to learn evolvable genotype-phenotype maps. And so we use the word evolvable in the sense of evolvability. So let's just jump in and talk about what evolvability is and why we want it. So there's a lot of different definitions of evolvability in the literature, but there's kind of a general consensus around the idea that evolvability is related to the amount of viable variation available to the evolutionary process. And so we can kind of divide this question of evolvability into two parts and look at them separately. So looking at the types of mutational outcomes that we want to see with respect to evolvability, we want to see something more like on the left here than on the right, because we want high phenotypic variation to be available under mutation, right? We want to see lots of novelty. And again, comparing the left and the right here, we want outcomes that look more like the left than the right with respect to evolvability, because we want to have viable outcomes under mutation, right? We don't want dead elephants in this case. So the question of evolvability is really closely tied to the genotype-phenotype map. So let's take a look at that relationship with a hypothetical example here. So we've got a genotype space, which is arranged in a grid with the little lines between the individual genotypes representing single mutations. And then we have three possible phenotypes on the right. And let's consider the phenotype on the bottom, the red dashed phenotype, to be invalid or non-viable. So, right, we have an arbitrary genotype-phenotype map. Right, we can trace back the phenotypes, and now we have a mutational network connecting various phenotypes. So let's take a look at another example. Right, we can exclude the non-viable phenotype in our genotype-phenotype map. And now we have a mutational network where we can bump around as much as we want, and we'll always have we'll always have viable phenotypes. So this helps us with kind of the viability side of the evolvability question. Let's take a look at another example. Right, we trace it back. So now we have two separate regions of the genotype space that are separated kind of by a valley of non-viable phenotypes. And so if we start out, say, in the green region of the genotype space, it's going to be hard for us to make our way over and explore the blue region. So this kind of setup hinders the type of novelty and also, I guess, viability that we want to see under mutation. Looking at another example, right, we can also use the genotype-phenotype map to get ourselves a lower dimensional genotype search space, right? So this is, of course, the lowest dimension space that we want with respect to this problem, just the two interesting phenotypes connected by a mutation. So in evolutionary computing, we define the genotype-phenotype map. So what options are available to us? Well, we could use a direct genotype-phenotype map. However, this often comes with poor evolvability because it's kind of just an arbitrarily chosen direct encoding. By direct encoding, I mean a genotype-phenotype map where each phenotypic characteristic is encoded directly and independently in the genotypic encoding in the genotype. The second option, we could use a manually designed indirect genotype-phenotype map. However, this has some drawbacks. It's often labor-intensive to design these. It can be ad hoc and heuristic. And some indirect genotype-phenotype maps, especially kind of low-level developmental models, can become computationally prohibitive to evaluate. And there's no guarantee with respect to evolvability. We kind of have to design these by trial and error. So what's the third option? So before we get to the third option, we need to go to autoencoder bootcamp. And you're probably thinking, hey, autoencoders, I signed up to, I guess, watch a YouTube video about cool evolution stuff, not lame random things like autoencoders. Well, you're not the only one who thinks that, but we'll use autoencoders to do cool evolution things. So stick with it, and we'll get there, I promise. So we're going to talk about an autoencoder from a functional perspective. An autoencoder takes an input, you shove it through the autoencoder, and it tries to hand the input back to you. And a disclaimer here, even though a lot of the examples that we're going to be talking about to build our intuition revolve around face images, autoencoders aren't just for face images, they can be used on a wide class of problems. But why is something that just gives you back what you gave it interesting? Well, there's kind of two superpowers here. Autoencoders can compress input that you give them, and they can also remove noise from that input. And so there's two types of autoencoders, each specialized on one of these tasks, and we'll talk about each of them in turn. So first, the bottlenecked autoencoder, right? This one is for compression. You take an input, in this case an image, you feed it through the encoder section, you get a bottlenecked representation, a more compact representation of the input, and then the decoder translates that input back into, in this case, back into a face for you. So in order to get a better intuition for what's actually going on here, we're going to go through a walk in the latent space. Oh, I should mention, I'm going to use the terms kind of latent and bottleneck interchangeably here. When you hear latent space, think of the set of all possible bottlenecked encodings. All right, so we're going to go through a walk through the latent space. So we're going to walk from beard guy over to red or brown hair woman. So we're going to stick beard guy through the encoder portion of our autoencoder. It's going to generate a bottlenecked representation for us, and then we're just going to do a linear or an interpolation between the bottlenecked encoding of beard guy over to the bottlenecked encoding of this brown-haired woman, and we're going to use the decoder to visualize our progress along the way. So we start at beard guy, and we're going to walk over to this brown-haired woman, and then we can keep walking over, for example, over to a red-haired woman. So what I want you to notice here is this really interesting continual deformation of properties of these faces, like the pose, the hairstyle, the gender expression. It all changes really fluidly as we move through the latent space. So now let's talk about denoising autoencoders, right? Second type of autoencoder. Takes an input after we did something stupid to it, like obscuring part of this guy's face, shove it through the denoiser, and it's going to try to give this guy his nose back in this case. It tries to remove the noise from the image and generate a valid face image for us. So this is all fine and dandy, but what's under the hood? Deep learning. Yay, deep learning. So hot right now. For those of you who are Rip Van Winkles and have been asleep for a while, deep learning is just big artificial neural networks plus big training data. So let's talk about the second part of that equation, big training data. Right? If we want to train autoencoders, we need lots of examples of the types of items that we want to autoencode. And I want to make kind of a subtle but important point here, which is autoencoders learn to encode members of a class that's a subclass of a larger class of possible items, right? So in this case, we've been talking about face image autoencoders, right? Face images are a subset of all possible images. And so we need lots of examples of the class of face images in order to train our autoencoders. So we need pointy nose people and wearing hat people and mustache people, etc., etc. So now we get to the cool evolution part. How can we use autoencoders to learn an evolvable genotype-phenotype map? Well, let's think back to the latent space interpolation that we were just talking about. And say if I was trying to evolve faces, I would sure like to have kind of an arbitrary walk through my genotype space look more like on the top than on the bottom, which I put in a pixel space interpolation, right? Where not everything along the way looks like a face. So in the pixel space interpolation, you have to cross through on this arbitrary walk. You're walking through pretty deep fitness valleys where there are obvious reasons why these images don't look like faces due to ghosting issues. So how can we get this from a genotype-phenotype map? Well, what we're going to do is take an autoencoder, right? And we're just going to karate chop off everything except the end part, the decoder. And now our genotype space is going to be equivalent to that interesting latent space that we've been talking about. So to get a sense for what kind of evolutionary dynamic or the evolutionary implications of this, let's look at a really simple hypothetical example. So we have this ridge-shaped fitness landscape where X and Y are different genetic variables that we can change by mutation, and then the Z-axis, the height, is just representing fitness. Right, so we evolve a single population and ends up somewhere on our fitness ridge. We evolve multiple populations. They end up somewhere else on our fitness ridge, right? And now we're going to use these good examples, which are a subset of the larger class of all possible examples or all possible solutions. And we're going to use these as training data for a bottlenecked autoencoder. So, and then we're just going to chop off and use the decoder. So our genotype space, say, is going to be lower dimensional, say 1-dimensional compared to the 2-dimensional phenotype that we have. So as we move through the genotype space, right, we're going to track over the phenotype space, specifically the fitness ridge on the phenotype space, the interesting part of the phenotype space, because the autoencoder has learned the pattern of distribution of the phenotypes, and the latent space is just going to map us to the across the set of good solutions that we trained with, right? So let's take a look at another example. How can we use a denoising autoencoder as a genotype-phenotype map? Well, gee, if I was trying to evolve faces and my mutational operator did something stupid, like putting a white rectangle in the middle of a face, I would really like my genotype-phenotype map to do its best to at least give me an interesting face to evaluate, right? To try to reconstruct or fix obviously detrimental mutations. So to use a denoiser as a genotype-phenotype map, right, we're just going to shove the genotype in one end and the phenotype is going to come out the other. So let's look at another hypothetical example, right? A 2-dimensional fitness landscape again. We evolve a single population, it ends up on a fitness peak. We evolve multiple populations, they end up on different fitness peaks. And now, if we train our autoencoder, hopefully it'll start to learn the regularities and the distribution of these local fitness peaks, right? And so what the denoiser is going to do is you give it an arbitrary genotype, and it's just going to map you to a genotype being the hollow circle, and it's going to map you to the nearest fitness peak, the solid circle, right? Because it's learned the regularity of distributions of the interesting solutions that it was trained on, the good solutions, and it's going to try to map you towards the nearest place where it thinks a viable solution might be. So if we mutate, right, we're still getting mapped back to the same phenotype. We're mutating and mutating and mutating, and eventually we're going to cross a threshold where these these mutations have been buffered for a while. Suddenly we're going to have a large phenotypic change when we get mapped to a new fitness peak. So we've already touched on this a little bit, but we need examples of good solutions to train the autoencoder, right? Because it needs examples of the class that we want to autoencode. So how can we get training data? How can we get good solutions? Well, we can do repeated evolutionary runs like we talked about, or we can also perhaps harvest pre-existing data. For example, if we're trying to evolve faces, there's plenty of face images out on the internet. So just go grab some, train your autoencoders, and then you're off to the evolutionary races. So now I'd like to move on to discuss the first example, or the first problem that we demonstrated this approach on in our paper, our GECCO paper. So the first problem, we call it the 100-legged table problem, right? So the phenotype is just a vector of 100 float values, where each float value represents a different leg length. And we take fitness as the inverse of the standard deviation, or the negative negative value of the standard deviation of those leg lengths. So basically, the best fitness here is a level table. And this is a rugged fitness landscape because any level table becomes a local fitness peak, right? If you adjust any one leg of the level table, you're going to be destabilizing the table. You're going to be increasing the standard deviation of the leg lengths if you are at a perfectly level table. So to prepare the autoencoders, we made training data by evolving different populations using a direct encoding, where each individual leg length of the hypothetical table was encoded separately, and then we trained the autoencoders. And basically what's going on here intuitively is the bottleneck autoencoders learning to map all one value to all the leg lengths, right? Because it can just, the local fitness peaks are all level tables, and so it's basically figured out that it's only seeing level tables, so it can just represent the all the leg lengths of a table with just a single height value, basically. The denoising autoencoder is kind of learning to take the average of the leg lengths that it's seeing, because we take level tables and we disturb them a little bit, and guess the original set of leg lengths as just the average of the leg lengths that it got given. So now we want to evaluate our method's ability to systematically explore the set of tables and respond to a slight selective pressure, in this case penalizing tables for being tall, right? This new term in blue just penalizes based on the mean value of the leg lengths. And so levelness is still essential here, but short tables tend to be favored over tall tables, right? And so if we start with a population of tall tables, how well can short tables evolve under these different genotype-phenotype maps? How can we more systematically explore the set of phenotypes, right? So if we use a direct encoding, which is the only line I have here at the moment on this graph, you can see generation on generation, we get stuck at just the tall tables that we started with. However, with the denoising genotype-phenotype map, you can see we're making slow and steady progress towards the global optima of the zero table height, or the 0 units tall table, right? And the bottleneck encoder, where we're just evolving a single value of the table height that's getting mapped back out to all the leg lengths, very trivially finds the global optima of the zero height table, right? So that's a bit of a proof of concept, really toy problem. So we also wanted to demonstrate these techniques on something a little bit more complicated. So the second problem that we talk about in the paper is the Scrabble string problem. So in this problem, the phenotype that we're interested in evaluating is a 100-letter string with the characters A through Z and the space character, right? And the fitness, we calculate it as the number of characters contained in valid Scrabble words. So in order to have good fitness, you need long, valid words. However, this is a rugged fitness landscape because short words are difficult to combine without causing a whole set of letters to become invalid, incurring a large fitness cost. And so we only worked on the denoising genotype-phenotype map for this problem. And how we apply it basically is, as you can think of it, as like a spell checker, right? So the denoiser sees a sequence of something like 10 characters, and it tries to guess the correct value or the correct character for the character at the very middle of the range of characters it's looking at. So you kind of think about sliding this spell checker along your string of 100 characters, and it's trying to correct any spelling mistakes that it's seeing along the way. And so we trained this by evolving a bunch of strings with a direct encoding, which of course ended up with a bunch of short words. And we corrupt a letter sometimes in the training data that we're giving this autoencoder. And the autoencoder tries to guess the original letter, and we check the guess against the correct answer, and if it's wrong, then we adjust the autoencoder right through backpropagation. And so using this encoding compared to the direct encoding, which I have here right now, I'm showing decrease in fitness by mutational step, right? You can see we have less rapid decrease in fitness by mutational step using the denoising autoencoder. So this is helping to buffer deleterious mutations is kind of the interpretation. And we have 95% confidence intervals that are shaded, but they're really tight, so they're difficult to see. We can also look at phenotypic divergence under repeated mutations. So the novelty, kind of the second part of the evolvability question, right? Compared to the direct encoding, the denoiser, we see greater, more rapid phenotypic divergence by mutational step. Again, 95% confidence intervals are shaded. So we can put these two considerations together in a diagram referred to as an evolvability signature, where we can co-visualize on the y-axis novelty and on the x-axis viability. And you can see the compared to the direct encoding, which is the green dashes, the denoiser, which is the solid blue line, we see greater phenotypic distance with less, at the same time, with the same mutations also seeing less fitness difference. So we're kind of having our cake and eating it too with respect to both sides of the coin of evolvability. So wrapping up here, I want to touch on challenges and solutions, or challenges faced by this approach, and maybe some potential solutions, right? Because this isn't a silver bullet. There are some really steep hurdles that we need to tackle in order to actually apply this approach. So one question is, if we already need good solutions to train, why should we use this approach in the first place, right? We already have good solutions, so let's just use those. So the idea is that by using these autoencoder genotype-phenotype maps, we can more systematically explore the set of local fitness peaks than we can by just doing a bunch of replicate evolutionary runs. So hopefully with this evolvable genotype-phenotype map in hand, we can get even better solutions than we had in the training set. And if, on the other hand, if we can't get any good solutions in order to train our model, perhaps we can try to get there through some iterative bootstrapping, where we evolve we evolved training data, but they're kind of crap solutions, but we still train an autoencoder, and then we use that to evolve more solutions, which are hopefully a little bit better, and then we train our autoencoder and hopefully, repeat the cycle and bootstrap our way up to having good solutions in an evolvable encoding. Another concern here is that AutoMap might only generate the good solutions that were used to train it. And I think there is some validity to this concern. However, one of the neat things about deep learning is that it can often generalize beyond training data, right? That's what makes it so powerful. So you can kind of think of this in terms of mixing and matching elements of good solutions that were in the training set in order to generate new solutions that weren't in the training set. So you can find hopefully better solutions than were in the training set. However, if your training set does systematically exclude, certain potential solutions, then your autoencoder will kind of miss out on those. One thing I kind of think about with respect to that Scrabble problem, right, is if you're using the direct encoding, you tend to evolve shorter words. And so the spell checker is basically going to learn to spell check expecting shorter words, tending to expect shorter words. So if you can find a way to get a better sampling of the set of good solutions, you can probably get around this problem mostly, but there will still be concerns. Another concern is that with an indirect genotype-phenotype map, parts of the phenotype space become totally inaccessible. This is an inherent concern with indirect genotype-phenotype maps, and the point here is that hopefully the parts of the phenotype space that you don't have a corresponding genotype for, right? Hopefully these parts aren't the interesting parts, so you're just kind of getting to exclude them from your search for free. And we might be able to address this by using something like the hybrid approach that was proposed by Clune et al., basically evolving with an indirect map until you reach convergence and then switching over to a direct genotype-phenotype map in order to polish your solutions and optimize and get to the parts of the phenotype space that you weren't able to access with the indirect mapping. Another concern, I especially felt this, running these experiments, is that manual genotype-phenotype map design is difficult and highly heuristic, but we all know that we all know that deep learning is black magic, right? So again, hopefully this might, even though we have to do kind of black magic manual labor, either way, hopefully we can get better quality outcomes in some cases than manual design, right? Another valid concern is the computational cost of making training data. We need big data to train these, so that means doing a lot of evolution, and hopefully parallelism can provide a way to quickly generate a lot of training data, even though you need a lot of hardware to do it. And finally, there are some kind of inherent performance limitations to autoencoders, as you probably saw in those face images, right? The input the output of these autoencoders sometimes isn't exactly the input that you're putting in, because there's some constraints on the resolution or what have you in the face images, or the reconstructions aren't totally convincing in the face images. So artificial neural network autoencoders are an active area of research. So this method stands to benefit from continuing advances in that field. And also, this kind of concept isn't necessarily directly tied down to the artificial neural network implementation of autoencoders. So if someone finds a clever, better way to do autoencoders, this method could also benefit. So with respect to the next steps that we want to take this research on, we of course want to demonstrate our method on more challenging problems, moving beyond proof of concept. And we want to show, in addition to showing effects on evolvability, like we did here, we also want to demonstrate that we can find better quality solutions using these autoencoder genotype-phenotype map methods than you could otherwise. And one domain we're considering working in is soft-bodied robots, but if people have other ideas where this kind of approach might be useful and interesting, feel free to reach out and tell us. We'd love to hear. Another thing we could look at is using generative adversarial networks in place of autoencoders. There's been some really awesome work with these in the image kind of tasks that are popular in lots of deep learning literature. These are kind of the inside out and backwards version of autoencoders. And I think that these could be used for a similar effect. And I also really want to put this kind of methodology in conversation with recent work synthesizing learning theory and evolvability theory. I think it would be really interesting to look at this methodology more deeply in light of the synthesis, and perhaps this methodology could also feedback and be useful and interesting to the theoreticians. All right, with that, I want to point you towards our Open Science Framework page, where we have everything you could shake a stick at with respect to this research, including our source code. I want to thank my co-authors, Dr. Bonzoff and Dr. Ofria, and also want to acknowledge Dr. Ofria as my academic advisor. I want to thank the software, the institutions, and the resources that made this possible. And I'd love to take your questions, probably commenting. I don't know if it'll alert me to comments, but please reach out to me by email or on Twitter. Let me go and show those again. I'd really love to hear any questions you have or suggestions, comments, what have you. Drop me a line. All right. And with that, I will just page through my references so that you can see any that you're interested in. And that'll be that. Thank you for your time.